Well, then we might as well get started. Looks like a lot of people are already here. So we'll just go through the practice questions, and I'll try my best in each case to make it clear what you need to know in order to solve the problem. So the first problem is mass spectrometry. And this particular format is I give the mass spectrum and you need to pick out fragments. So I gave an example of an answer that would receive full credit. The way you do it is you put the structure of the fragment, it should be something with a plus charge, and then where it shows up on the spectrum, m over z equals whatever. And you can see already the molecular ion at 114. So you actually know what the compound is. And the idea is, can we give any fragments? So we need fragments other than the molecular ion and other than the peak at 29, which is the ethyl cation. So we already know the structure of this compound. I don't know where I can fit this. So there's the structure of the compound. And in class, we discussed how it is that ketones fragment. We said they undergo alpha cleavage, which means breaking either this bond or this bond, though in this case, it doesn't matter which because the compound is symmetrical. So that's going to be one bond we can break. We also said when it comes to alkyl chains, to break along the carbon-carbon bonds. So we get the ethyl cation by this bond breaking, which is the methyl cation by that bond breaking. And methyl group is 1 carbon and 3 hydrogens. So it's 12 plus 3 is 15. And what do you know? I can actually see a little peak at 15. So it's reasonable to assign that to the methyl cation. So you write CH3 plus at m over z equals 15. And it would make sense that we could also see the propyl cation with 3 carbons at 43. The way you get that is the propyl cation is C3 has 3 carbons and 7 hydrogens. 3 times 12 for the 3 carbons is 36. 36 plus 7 for the 7 hydrogens makes 43. And that's actually the base peak, is the propyl cation. So you write CH3, CH2, CH2 plus m over z equals 43. Another cation you can get is by breaking this bond here and putting the plus charge in the carbonyl carbon. That's an alpha cleavage. So you get CH3, CH2, CH2, C double bond O with a plus charge on carbon. That's another fragment that we get. And let me draw that over here. Plus charge on carbon. You could also draw the other resonance form with a triple bond between the carbon and the oxygen and the plus charge on oxygen. Perfectly acceptable. It's the same thing, just the other resonance form. And that one has 4 carbons. So 4 times 12 is 48. It has 7 hydrogens. 48 and 7 is 55. Plus the oxygen is 16. 55 and 16 is 71. And we do indeed see a peak at 71. So in order to put it down as a fragment, you actually have to see it on the spectrum. But in class, we went over rules for how to find fragments in a mass spectrum by how molecules fragment. And actually, I found another one at 99. It's actually this one. So that's 4 fragments right there, and I'm probably missing some. And they only needed 3 in order to get full credit. So the way you do it is by breaking bonds and adding up the masses of the fragments that are left, and then hunting for those peaks in the mass spectrum, just like we did in class. So that's how you answer that question. The next question is about IR spectroscopy. I'm juggling a lot of documents in this one. So first of all, would we have to draw 3 structures? I'm not going to say how many or if the same format is on the exam. I can't give details like that about your exam.
Sure.
I was wondering because the question asked exactly 3, so I was wondering if. So
Right,
the question
I'm
said,
drawing 4 for teaching purposes to show you other possibilities.
okay,
So in other words, to get credit on this question, you could draw any 3 of those 4, and I'm probably missing some. That's the only reason I drew 4 structures, is to show you the choices that you had in answering that question. And those were just the ones that I could think of. But on the exam, you will need to follow the directions. I don't promise they will be exactly like these or that it will be exactly the same format. But on the exam, you will just need to follow the instructions. Next is the infrared spectroscopy question, and the first infrared spectrum is over here. And the first thing I notice is there's a carbonyl. That's at about 1720. So that narrows it down to B or D. And when you look at the CH stretches, there are some that are above 3,000 wave numbers. That means we have some CH stretches that are on sp2 hybridized carbons. So it can't be D, because D is only sp3 hybridized carbons. So it has to be B. This would have some CH stretches on both sp3 and sp2 hybridized carbons. So spectrum S is B. Spectrum T, the alcohol OH stretch really jumps out at you. Nothing else has that smooth parabolic peak at about 3,400 wave numbers. So what are our possibilities for alcohols? The only alcohol I see is A, so it has to be A. C is not an alcohol. C is a carboxylic acid. So that one was pretty straightforward. Spectrum U looks like it has all of our CH stretches below 3,000 wave numbers. And no carbonyl, no alcohol, no nothing. So it looks like we have just an alkane. And the only one that fits that description is E. And finally, spectrum V looks real similar, except there's some CH stretches above 3,000 wave numbers. So there's no carbonyl, no OH, no other functional groups, just hydrocarbon, but including some sp2 hybridized carbons. And the only one that fits that description is F. So you see how on this type of problem you can narrow down which structure to take based on the functional groups that you see and also the functional groups that you don't see.
That peak in the middle, that's like between 1,500 and like 1,700. Could we say that that's a C double bond C?
This one, I suppose it could be, or do you mean this one?
That one, the one that's like at like about 1,650 or 1,700.
It's
That
possible.
one, yeah. That one, yep.
I would expect it to be a little stronger, but it's possible.
So can we say that C double bond C would be that like C double bond in that ring structure of F?
It's entirely possible,
Okay.
but I'm picking it out mostly by the CH stretches. C double bond C can be hard to pick out.
Where would
CH
where are the CH3 stretches in structure F?
The CH there are no CH3s, there's only CH2s, and they're all sp3, and they're going to be all below 3,000 wave numbers. But this
Okay.
is above 3,000 wave numbers, so it has to be on an sp2 hybridized carbon. It's really the only major difference between this spectrum and this spectrum. We
Gotcha.
also
Thank you.
know it's not aromatic because I don't see the overtone bands in this area. I'm sorry, I interrupted you.
No, you're fine.
Oh, okay. Well, that's it for this page. Let's move on to the next page. So same idea, matching the carbon NMR spectrum to the structure. And there's 4 spectra and 6 structures. So when we look at the first spectrum, I see 5 lines. There's 5 peaks here, one of which has to be a carbonyl. Nothing else shows up above 200 parts per million besides a carbonyl, C double bond O. So we're looking for a compound with 5 different carbons, one of which is a carbonyl. And there's only one compound that fits that description, which is H. G and J are both carboxylic acids, and those carbonyls show up at more like 170 or 180. So it has to be H.
What about I?
I has only 3 types of carbon. These 2 methyls are the same, CH2s are the same, and then you have the carbonyl.
Okay.
Can't be
So
I, it has to be H.
I only has 3 peaks and then H is 5.
Right.
Gotcha. Thank you.
Now, spectrum X, there are exactly 5 peaks between 120 and 135 parts per million. That means that if you include the one at 141 or 142, there's 6 peaks in the aromatic range. So you need to know where aromatic carbons show up. I also do see a carbonyl for a carboxylic acid, plus 1 other peak in the alkyl range. So it looks like we've got an aromatic ring where all 6 carbons are different. plus a C double bond O, plus some other carbon that's just an alkyl type carbon. There's only 2 compounds with aromatic rings. In compound G, all 6 of those aromatic carbons are different. They're all bonded to something different. They're all different distances away from the carboxylic acid functional group. In J, we would expect to see only 4 aromatic carbons. This one, the 2 that are ortho to the carboxylic acid, which are equivalent, the 2 that are ortho to the methyl group, which are equivalent, and the carbon that's bonded to the methyl group. So for J, we'd see 4 peaks in the aromatic range instead of 6. So spectrum X has to be G. The next one has only 3 peaks, and I don't see any carbonyls or anything like that. So there's 3 types of carbon, and the only ones without carbonyls are K and L. How many types of carbon does K have? 1 for the CH3, 2 for the CH2, 3 for the quaternary carbon, and 4 for the CH3s, which are all equivalent. So for K, we would see 4 peaks. What about L? L has this type of carbon that's next to the oxygen. These 2 CH2s are the same. It also has these 2 CH2s, which are the same as each other, but different from the first CH2s because they're a different distance from the oxygen. And then there's this unique CH2 on the other side of the ring. So L would have 3 carbons, one of which is alpha to oxygen, and that would be this most downfield peak that shows up just shy of 70 parts per million. Very typical range for carbons that are alpha to oxygen. So I think Y has to be L. And then last but not least, someone asked about compound I before. This one is compound I. It is 3 types of carbon, one of which is a carbonyl, and then 2 of which are alkyls. And again, these 2 CH2s are the same. The way you know that is if you replace a hydrogen with chlorine on either one of these carbons and name it, you'll get the same name. And then, of course, the 2 CH3s are equivalent. They're the same distance from the carbonyl. So spectrum Z is compound I.
One more time, could you count the number of peaks on J? Because I'm not counting 4. I'm counting 5. Yeah, I'm counting 5 peaks on J.
Well, 4 aromatic carbons. There's this one. Then there's the 2 that are ortho to the carboxylic acid. They're the same as each other. Then there's the 2 that are ortho to the methyl group that are the same as each other. That's a 3rd column. And then you have the one that's attached to the methyl. So there's more carbons than that, but there's 4 aromatic carbons.
Is that carbon not equivalent to that other aromatic carbon, or like that? How do I explain it? All right, I think the carbon that's with the methyl group attached,
Right,
and then the
one.
carbon with that carboxyl group attached, are those 2 carbons not equivalent with each other?
No, because one's attached to CH3 and one's attached to a carboxylic acid functional group.
So they have to be attached to the same functional group in order to be equivalent. Correct?
Right. If they were both
Gotcha. Thank
groups,
you.
then they'd be equivalent.
So totally, how many carbon peaks would J have? Like
Would have 1 for the carbonyl, plus 4 for the aromatics brings us up to 5, plus 1 for the CH3 brings us up to 6.
Cool. Thank you.
So that's how I would approach that problem. So you have to know something about typical chemical shifts, both for carbon NMR and for proton NMR. Sorry?
I just said thank you. Like,
oh, okay.
Thank you. Yep.
The next one refers to the little bit of ultraviolet and visible spectroscopy that we did on the first day of class. And what you need to know is the more conjugated double bonds are in the molecule, the longer the wavelength of maximum absorption is. Longer wavelength, lower energy. And so the highest value of lambda max would be for the most conjugated compound. The lowest value would be for the least conjugated compound. Meow yourself. My cat's talking to me. So the one with the fewest conjugated double bonds would be B. That is only one. Then C has two conjugated double bonds. That's going to be a slightly longer wavelength. Then D has three conjugated double bonds. That will be a slightly longer wavelength. And the longest wavelength of all would be A, because it has four conjugated double bonds. So that's the order that I would expect them to show up in. I certainly don't expect you to memorize any particular absorptions. I certainly would never draw you a compound and say, where does it absorb? Just to know that the more conjugation is in a molecule, the longer the wavelength of maximum absorption, or the lower the energy. I'm sorry, lower the energy. Longer wavelength, lower energy. Energy and wavelength are inversely proportional. Questions on that page? All right, next we have some questions about aromaticity and drawing resonance forms, which is certainly fair game for you guys. This first question is asking about this intermediate and asking for three other resonance forms. So you need to be able to shift bonds around. One other resonance form puts the plus charge over here. And then another resonance form shares the plus charge on the oxygen, which is able to donate electron density by resonance. So you get something that looks like that. And then the last resonance form puts the plus charge on the other side of the bromine. I'm struggling. Over there. Oh, what have I done? Plus charge over here. And of course, we'd still have that lone pair on oxygen. There we go. That's better. So then it asks, which is the best resonance form? The best resonance form has the plus charge on oxygen, because putting the plus charge on oxygen means you're putting it on an atom that's obeying the octet rule. I think we're actually done with that part. So this one should be circled. That one probably makes the largest contribution to the overall molecular orbital picture. You're never putting a plus charge into carbon. When carbon is a plus charge, it only has 6 electrons around it. And the next one has an electron withdrawing group on it. And we're investigating what would happen if it added the bromine from the para position, which you wouldn't expect to happen with an electron withdrawing group on the ring. Electron withdrawing groups are meta-directing.
I have a
Whereas,
question.
sure,
I have a question on the question we just did. I thought positive charges would not want to go to the electronegative atom. Like I thought they would be want to be on the less electronegative atom, in this case carbon.
well, my understanding is, although oxygen is more electronegative, it's unique in that it's the only one that still has 8 electrons around it. So my understanding is that takes over. Because you can't distinguish which of these three is best. They all have the plus charge on a carbon atom. So I think that's the best answer.
Okay, thank you.
Now for this one, if it weren't for the one with the oxygen, then this one would be the best answer, because that is the plus charge in a tertiary carbon. But I think the oxygen wins out. Now, if the oxygen were not there, then this one would be the best answer. And there would only be 3 resonance forms. So we need to do the same thing with this one. And drawing these intermediates without it being drawn for you first is something that I expect you can do. So there is another resonance form. And then there's another one with the plus charge on the other side of the bromine. And I think of all of these, even though it's on a tertiary carbon, this one is the worst one because it has the plus charge right next to a very electron poor atom. That carbon is very electron poor because of the 3 electronegative chlorines attached to it. So I think that one's the worst one. I think these 2 are equally good or equally bad. So I think that one's unique. Good, and last but not least, circle the species that is aromatic. There is exactly one such species. Well, this one, I believe, has 12 pi electrons, 2, 4, 6, 8, 10, 12. 12 is the wrong number, so it's not that one. 12 doesn't fall into the series 2, 6, 10, 14. This compound has the same problem. It has 8 pi electrons, so it's not aromatic. This one has only 4 pi electrons. That also doesn't fall into the series 2, 6, 10, 14. And worst of all, a 5-membered ring is too small to be able to be flexible. It's rigid. So this one is forced to be planar. That's actually an anti-aromatic cation. But it's only asking whether the species is aromatic or not. So we can rule out these 3. The next species is pyridine. That's a structure you should know. Pyridine has 6 pi electrons. The lone pair on the nitrogen, we drew this one in class, is in an sp2 hybrid orbital. So pyridine has 6 pi electrons. And in case you weren't sure, you can look at this one. This one might have 6 pi electrons, but it is an sp3 hybridized atom right there. So we can rule out that one. All of the ring atoms need to be sp2 hybridized in order to be a candidate to be aromatic. So the last one's not aromatic either. So it has to be pyridine.
I have a question on the previous question that we just did. Could you explain why the middle one is the worst one again?
Because you're putting a plus charge right next to a very electron poor atom. The chlorines are pulling electron density away from the carbon. It's like it is a partial plus charge. And you're putting the plus charge adjacent to that. With the other 2 resonance forms, you're not doing that.
But would not matter if it's the most stable carbocation because it's tertiary?
Um, In a word, no, I still think that one's the least stable. This was like what we did in class, except in class we had nitro groups here.
Okay.
And with the nitro group, it's very clear. The nitrogen has a plus charge on it, so you have two adjacent plus charges.
Mm-hmm.
The trichloromethyl groups don't go quite as far as the nitro group. But you still have an atom with a partial plus charge. And I think that overrides the fact that it's tertiary.
Okay. Thank
So
you.
the way you know what you need to know about these questions is by looking at what's attached to the aromatic ring. And remember, if there's an electron-rich atom that donates electron density by resonance, that one is going to give rise to the most stable resonance form, even though really there's only one structure. But the most favorable resonance form will have the plus charge on the electron-rich atom. And then, if you have a case like this where you've got an electron withdrawing group on the aromatic ring, these structures are explaining why we do not get attack from the para position when there's an electron withdrawing group. If we attacked instead from the meta position, you'd never be putting any plus charge next to this electron poor carbon. It would be on other carbons in the ring. So that's the explanation for why meta-directing groups are meta-directing. It's because you're never putting any plus charge next to the electron poor atom, and so you get a better stabilized carbocation, or maybe it's less bad stabilized, something like that.
Okay. Thank you.
Any other questions on this page? Oops. So many documents to juggle. Now for this one, we're filling in the products. The first one has a chlorine on it, which is orthopara-directing. It wants to put the new group in one of these three positions, either ortho to the chlorine or para to the chlorine. And the methoxy group is in agreement. It wants to go also ortho or para to the methoxy. These two positions are ortho. This position is para. So the new group wants to be in one of those three positions. And then you need to recognize this reaction. The reason I knew this was an electrophilic aromatic substitution was from the reagents. So you need to recognize those as the reagents for electrophilic aromatic nitration. It replaces an aromatic hydrogen with an aromatic nitro group, NO2. And so then the question is, which of those three places is the best? Where are we going to get the major product? I think we can all agree it doesn't want to go here, because that's between two groups. There's the least room there. So it's between these two. And remember, in class, we said that you want to put the new group closer to the smaller group. And the way you know which group is smaller and which group is larger is smaller groups have fewer atoms, larger groups have more atoms. The methoxy group has 1, 2, 3, 4, 5 atoms in it. And the chlorine is just one atom. So I believe the nitro group would go ortho to the chlorine. I think
Could we
that's
also put it? Could we also put it to the left of the OCH3?
no, because the OCH3 is bigger, and the major product would have substitution next to the smaller group.
It's orthopara, correct?
Right, but this is asking for the major product.
Oh, okay, got you.
You would only put both if it asked for both products. But this is asking for the major organic product. That's one structure. In
Thank you.
principle, you could get it in all three locations, but I think that's going to be the major product. Sorry?
I was just like, got it. Like, yep, sounds good.
Okay. This reaction we did in class today, and actually we did it last semester. This is using excess NBS, so it's going to replace all benzylic hydrogens with bromines. There's two benzylic hydrogens here. Those are going to get replaced with bromine. And then this CH3, that's three more benzylic hydrogens. So that would become CBr3. If it were just one equivalent of NBS, that wouldn't be a very good question because you'd get a mixture. But basically, if it just says NBS, without saying excess, it means one equivalent. That's best practice. If it doesn't specifically mention excess, then usually that means one equivalent. At least that's what it should be. I've noticed sometimes active is a little sloppy about that. But this specifically says excess, so it will replace all benzylic and allylic hydrogens with bromines. The mechanism goes through a radical chain mechanism. And the next one we also did in class today. This is the same thing as just KMNO4 and H2O, same reaction. Sometimes we use a basic solution with KMNO4. And remember what we said? We said that we'll oxidize the carbon next to the benzene ring to a carboxylic acid functional group. And any other carbons in the chain, if there are any, get oxidized to CO2. So the major organic product will be the carboxylic acid, and the chlorine just goes along for the ride. So what you need to know is potassium permanganate and also sodium dichromate oxidize the carbons in alkyl groups as long as the benzylic carbon has at least one hydrogen on it. If the benzylic carbon is quaternary, then there's no oxidation. We gave an example in class today where there was a tert-butyl group there, and that does not get oxidized. But that carbon that I've just highlighted is a CH2, so it has at least one benzylic hydrogen, 2 to be exact. So the carbon that I've highlighted gets oxidized all the way up to a carboxylic acid functional group, which is as high as you can go, and the other two carbons just become CO2. So I think this benzoic acid derivative is the best answer. The next one, I would expect you to recognize the reagents for Friedel-Crafts alkylation. And actually, in truth, Friedel-Crafts reactions don't work real well when there's an electron withdrawing group on the ring. But the electron withdrawing group has a carbonyl directly attached to the benzene ring. We said that those are meta-directing groups. So I think the best answer has the tert-butyl group meta to the ester functional group.
Can we draw that in the other meta direction? Sorry, position as well?
Not only would I not take off points, I wouldn't even notice the difference.
Sounds good. Thank you.
Which means you need to become familiar, not you personally, but you guys need to become familiar enough with the material that you see them as the same thing and you're secure. And the next one is actually a reaction from chapter 8. So I expect you still remember all the reactions from last term. MCPBA is a peroxy acid. And in chapter 8, we said peroxy acids react with alkenes to give you an epoxide. So the epoxide has the three-membered ring. Since both carbons are chiral, we need to show stereochemistry. And you could either pick the one where the epoxide is wedge bond and the methyl group is dotted bond, or the enantiomer, which is the epoxide with dotted bonds and the methyl group is a wedge bond. Either way. And that's pretty much it for that page.
I have a question about the potassium permanganate reaction.
Right.
So if there are only quaternary substituents on the compound, then would you prefer us to put no reaction, or do you want us to just draw the exact same starting structure?
I will not put one on the exam for which it's no reaction.
Okay, thank you.
Not purposely, anyway. If you really think it's no reaction, put no reaction. But I would not purposely do that. I ask in this format of questions for one structure, and I have one structure in mind. Other questions?
With the CH2Cl2, like the carbene intermediate at the bottom, that wouldn't play
No,
into.
there's no carbene, that's the solvent.
Okay, yeah.
Epoxidations are done in dichloromethane solvent. The oxygen comes from the MCPBA.
All of this.
MCPBA looks like this. That's MCPBA.
For the
question.
NBS reaction, what would it look like if it was just one equivalent instead of excess?
You'd get a mixture. You'd get some bromine here and some bromine here. It would not be a good question.
Okay, thank you.
All right. In this format of question, you need to fill in the reagents. And in the first reaction, we're going from an aromatic ring to a cyclohexane. And that's another reaction that we talked about just today. There really were a lot of questions from today's lecture on this exam. And this is a hydrogenation reaction. The way you know that is we've added 6 hydrogens, and we've reduced the aromatic ring to a cyclohexane. We said how to do that in class today. Excess hydrogen and either rhodium or platinum. You can write excess H2RH or excess H2PT. Either way, both would receive credit. And you'll notice you get the cis stereochemistry from that hydrogenation. The next one is a nucleophilic aromatic substitution reaction. The way you know that is because you're replacing a halogen with another group. And actually, in one of my classes today, I said hexafluorobenzene was a really good substrate. for nucleophilic aromatic substitution. And the other one, I didn't get a chance to give this example. So what we're looking for, is something that will put this group onto the aromatic ring. And we already know that sodium methoxide, NaOCH3, will replace a halogen with OCH3. NaOET will replace a halogen with the ethoxy group. So this is the same thing, except it's an isopropoxy group. So you want sodium isopropoxide, or you could just write O- there in isopropanol solvent. You want to match the alkoxide group to the solvent. Otherwise, I'd be worried you'd get a mixture. So those were the only two of this format in the original exam that I could include for us. So you could tell there's space for more questions, but they were reactions that we haven't had yet. These were the only two that I could include on this exam for you guys.
Did you say we would have to know the solvent underneath, like the
Yes.
OH? Okay.
Yep. And the way you know that is because when we used NaOCH3, we used CH3OH. When we used NaOET, we used ETOH. The solvent matches the alkoxide. Actually, also, when we used NaNH2, we used NH3. So the way you know what to put for the solvent is you look at the anion you're given and you replace the alkali metal with a hydrogen. You always want the anion to match the solvent.
For the first problem, would we have to put excess or could we just put H2 and then the
H2
metal?
would lose points because it means one equivalent. You could put either excess H2 or 3H2. You need at least 3 equivalents to get the 3 pi bonds. 1, 2, 3. Does that make sense? You would get partial credit, but it's not 100% correct.
Okay, so you said it would be 3H because it has 3 pi bonds, but if it had more than that, would we put how many hydrogens are equal to that many pi bonds?
Right.
Okay.
So you need at least 3 equivalents, or you can just write excess. If we have time, I'll make up more questions with this format, since I only had 2. And now we get into the mechanisms. The first one is the reaction of nitric acid with sulfuric acid to give the nitronium ion. And the first step starts with the OH on the nitric acid, picking up the proton from sulfuric acid and putting the electrons on oxygen. and that oxygen becomes protonated. And then the electrons fold in from the O- to make a double bond to nitrogen. And then we have to break this bond also because nitrogen can't have more than 8 electrons around it. So that's the driving force for this reaction, is losing water as a leaving group. And that gives you the nitronium ion. So only 2 steps for this one. This is just part of the mechanism of electrophilic aromatic nitration. But the directions say to account for formation of the product shown from the starting materials shown. So it doesn't say to show anything else. So with this, we're done. I could have had it do the entire mechanism, but all we had here was going from nitric acid to the nitronium ion. And we can review that mechanism if there's time. That is the entire mechanism of electrophilic aromatic nitration. In the next one, if you look carefully, we're replacing a halogen with another group on an aromatic ring. In class, we said today that's the sign of a nucleophilic aromatic substitution. You also know it's a nucleophilic aromatic substitution from the reagents. Recognize NaNH2 as NH2-. That's a nucleophile. It's got a minus charge. It's an electron-rich species. So we start the reaction. With NH2-. Adding to the carbon that bears the halogen. And again, you'll notice I did not even write the sodium. So NH2- attacks over here. We break the carbon-carbon pi bond and put the electrons on the carbon next door. Remember, these reactions are neither SN1 nor SN2. Can't make it quite as pretty as I would like, but you get this carbanion intermediate, which is resonance stabilized. And then in the next step, the electrons from the carbanion come back into the 6-membered ring to reform the aromatic ring and break the carbon-halogen bond to lose halide as the leaving group. And that gives you your aromatic compound back. So also only 2 steps for this one. Questions on either of those mechanisms?
Was the second one not a Benzyme reaction?
Wait a minute. You're right. It is a Benzyme reaction.
Yeah, the answer key is a way different answer, so.
Sorry about that. It is a Benzyme reaction. And the way you know it's a Benzyme reaction is because the group attached to the aromatic ring is not electron withdrawing. So that's my mistake.
So it would only be an electron withdrawing group if it's a halogen, and since nitrogen is not a halogen, like we discussed in class, then it would be a benzyne.
Right, it needs to have an electron withdrawing group like nitro or C double bond O or something like that.
Oh, okay.
I didn't even notice the other group on the other side of the ring. I was not looking carefully.
So if it didn't have the other group, it would just go as a nucleophilic aromatic substitution. But
No,
since
if the NH2 weren't there, it would still be benzyne.
it'd still be benzyne. Okay. So when would it do the nucleophilic aromatic substitution? Because I thought the things over the arrow kind of denoted that.
The way you know it's a regular nucleophilic aromatic substitution that's not a benzyne is if you have at least one electron withdrawing group attached to the benzene ring other than the halogen.
Okay.
So those include things like NO2, C double bond O, C triple bond N.
Okay. Thank you.
We'll do an example like that too. So the first step in the benzyne reaction is pulling off the proton. And the electrons go onto the carbon atom. And you get that carbanion. Then the electrons in the carbanion come in between and kick out the halide leaving group. I wonder if it'll even let me put another bond here. Yes. So then when I look at the product, the other NH2 is para to the pre-existing NH2. So that tells me that I have to have the new NH2 attack para to it. The electrons go onto carbon.
Are there two lone pairs on the nitrogen, or is it just one lone pair?
On this one, there's two. The way you know that is because there's only two hydrogens attached.
Okay.
On this one, there's just one lone pair because there's three hydrogens attached.
Three hydrogens?
Sorry,
There's three. You said that there were three hydrogens attached?
NH2H.
Oh, gotcha. Yep, go.
And then we use our solvent to put the proton back on the aromatic ring. So the way you know what to put here is by looking at what you're given and finding the species that has the most extra hydrogens, the species that can best act as an acid. NaNH2 can't act as an acid. It already has a minus charge. It's a strong base. NH3 can act as an acid. To give you an example of an aromatic compound that would react in a normal electrophilic aromatic substitution reaction, we'll even put it ortho to it. And if you treated this with sodium hydrosulfide and ethanol, that would replace the bromine with SH. And the mechanism would go by I want the other resonance form. And so you'd get a resonance stabilized carbanion. And then the electrons would come back in and kick out the bromide leaving group, and you'd get the product. So the way you know which happens is by what's attached to the benzene ring. Electron withdrawing group, therefore nucleophilic aromatic substitution. In the other case, which I foolishly did not look carefully enough, there's no electron donating group, therefore benzyne. That's how you know. I'm sorry, no electron withdrawing group. And the way you know that NH2 is not electron withdrawing is because it has that lone pair on the nitrogen that can add electron density into the ring by resonance. So this is how you know. And I just, as I said, foolishly did not look at the other group. So learn from my mistake. Does that make it clear enough how you know which to choose? Any other questions on that? Wow, there's 35 people. It's a lot of people. More mechanisms on this page. The first one is an electrophilic aromatic substitution reaction. The way you know it's an electrophilic aromatic substitution is both by the reagents, which are strongly Lewis acidic, and the fact that you're replacing an H with another group. With a nucleophilic aromatic substitution, you're replacing a halogen with another group. With electrophilic aromatic substitution, you're replacing an H with another group. And so you remember in the Friedel-Crafts alkylation, what we start with is you show the carbocation that you get when pulling off the halogen and leaving a plus charge behind. So this is what we will start our mechanism with. Now, this is a secondary carbocation, and it can rearrange by a 1,2 hydride shift. And so that will surely happen before anything else. And that moves the plus charge over to the central carbon. Now the nitro group is meta-directing. So we're going to get attack from the meta position. It's going to get attached to the metacarbon. So you get this resonance stabilized intermediate. And then all we need to do to restore aromaticity is pull this proton off. So we need to figure out what to use as our base. And in order to do that, we look at what we're given. We're given this alkyl bromide and aluminum bromide. That means that we're going to form the tetrabromoaluminate ion. That is aluminum with 4 bromines and a minus charge. So if you'll recall from the class notes, this species loses a bromide ion, which picks up the proton. We break the carbon-hydrogen bond and push those electrons back into the six-membered ring to make it aromatic again. And you get the product. So that's how you would draw that mechanism. Questions on that one?
The reagent says AlBr3, but we wrote AlBr4 with a minus charge. Is that because you said it loses a bromine?
Yes, it loses bromide ion from the alkyl bromide, and that goes to aluminum.
Oh, okay.
The next, oh, other questions? The next one is also an electrophilic aromatic substitution reaction. We know that because we're replacing an H with a bromine. So whenever you're replacing an H on the aromatic ring, it's got to be an electrophilic aromatic substitution. And so the first step of electrophilic aromatic bromination involves the halogen attacking the metal halide salt that you're given. And you get a bromine with a plus charge and an iron with a minus charge. It got kind of covered up by the red nonsense, but this bromine is a plus charge because it is two bonds and two lone pairs. And so it's at this point that we take our ethylbenzene. Alkyl groups are ortho-para-directing. The product we're given shows attack from the para position, which is going to be the major product. So we attack that terminal bromine. So you get this resonance stabilized carbocation. After this, the tetrahaloferrate salt comes in. It loses a bromide ion. And remember, the bromine can also be chlorine. It's not necessarily Br. So please don't memorize Br goes here. It could be chlorine also. That picks up that proton. The electrons in the carbon-hydrogen bond go back into the aromatic ring. And that regenerates the aromaticity. And you get the product. That's how we showed the mechanism in the class notes. Make sense? Questions in either of those mechanisms? And the last page has some proton NMR spectra. And a combination spectroscopy problem. So the first spectrum has 4 types of hydrogens in a 6:4 to 4:1 ratio. The 6 hydrogen triplet looks like 2 CH3s with a CH2 next door. The CH2, the 2 H's in the CH2 are splitting this resonance into a triplet, 2 + 1 = 3 lines. Likewise, it looks like we have a CH2 next to the CH2. This is 2 equivalent CH2s. 2 times 2 is 4 hydrogens. And then it looks like we have another CH2 in the middle that has a chemical shift in the middle between those two. So this looks like CH2, CH2, CH3. Looks like we have a propyl group in 2 of them. 2 equivalent propyl groups. And the way I knew that was from the integration and also from the chemical shift. The chemical shift for this CH2, actually, that's a little bit more upfield than I would have expected. I would have expected that to be more like 3. But I'll take 2.6. So this CH2 has to be attached to an electronegative atom. So we're looking for something with 2 propyl groups attached to an electronegative atom. The only molecule that satisfies that is compound X. And then that explains this last 1H resonance over here that's quite broad. That 1H resonance is the hydrogen on nitrogen. So spectrum A has to be compound X.
Wait, where did the two, sorry, where did the 2 equivalents come from again?
Well, they're in a ratio of 3 to 2 to 2, but they're double that. So that means you have to have 2 equivalent groups.
And then what does the 1H broad tell us?
That's going to be the NH hydrogen.
Is it like, what does the broad mean?
Well, broad means that you can't see any splitting, and broad also means, do you see how much space there is between the 2 lines of the baseline?
Gotcha, okay.
It's a broad peak.
Sounds good.
And that's typical for OH and NH resonances. Spectrum B has 5 protons in the aromatic range, plus a triplet and a quartet in the upfield range. In class, we said that's a sure sign of an ethyl group. You have a CH3 with a CH2 next door. 2 + 1 = 3 peaks. And we also have a CH2 with a CH3 next door. 3 + 1 = 4 peaks. So we've got an ethyl group, and we've got an aromatic ring. That narrows it down to S and T. It has to be one of those two compounds. And what's going to decide it for us is what the CH2 is attached to. And if this CH2 were attached to an oxygen, like it is in S, remember OET means OCH2CH3. If the CH2 were attached to oxygen, we'd expect it to be at more like 4 parts per million. Instead, it's only at about 2.5 parts per million. That means that this CH2 is directly attached to the benzene ring. So spectrum B has to be compound T. And again, I knew that from the chemical shift of the CH2. I knew this was a CH2 because it's attached to the CH3, which gives us 4 lines. And then the other 5 aromatic hydrogens almost fall on top of each other. If I had to guess, I would say that the 3H resonance is going to be the 2 orthos plus the paraproton, which are similar electronically. And the 2 that are slightly further downfield are going to be the 2 metaprotons. That would be my guess. But this is a sure sign of a monosubstituted aromatic ring. Mono because benzene has six hydrogens. And so when you take one of them away and replace it with another group, you get only 5 hydrogens.
Does mono mean the same as singlet?
No, monosubstituted refers to the number of things that are the benzene on the benzene ring. Singlet refers to just having 1 peak on an NMR spectrum.
Okay.
And we have one in the next spectrum. The next spectrum has a doublet for 6 hydrogens. And that means that you have 6 equivalent hydrogens. The only way you're going to get that is with 2 methyl groups that have 1 adjacent hydrogen. So from this, we're getting two equivalent CH3s next to 1 hydrogen, and then attached to something else, attached to another carbon, most likely. So the 6 hydrogen resonance is these 2 CH3s, which are split into a doublet by the adjacent hydrogen, 1 + 1 = 2. And then the multiplet is going to be this 1H resonance. That has at least 6 hydrogens next door, so it's going to be at least 7 lines. So the 6H doublet and the 1H multiplet is an isopropyl group. And the isopropyl group from its chemical shift looks like it's attached maybe to a benzene ring or maybe to C double bond O. Because in both those cases, you'd wind up with something around 2.5 parts per million. So this bond over here, I think from the chemical shift has to be either to a benzene ring or C double bond O. Beyond that, we have a CH3 that has no adjacent hydrogens. I know that because it's a singlet. There are no hydrogens next door. 0 plus 1 equals 1. You get one peak. So these are the parts that we have. We're looking for something with a CH3 that's next to something that has no hydrogens and has an isopropyl group. The only compound that fits that description is compound Z. So both the CH3 and the isopropyl are attached to a carbonyl. The CH3 is a singlet because there's no hydrogens on the carbon next door. And then the isopropyl group is the 6H doublet plus the 1H multiplet. So spectrum C has to be compound Z. What about spectrum D? I see again a 6H doublet and a 1H multiplet. So that looks again like an isopropyl group. I see also a 2H resonance. That's a multiplet, has a lot of adjacent hydrogens. But what really stands out to me is this 1H triplet that's down here. Nothing else shows up between 9 and 10 parts per million, but an aldehyde hydrogen. So you need to know what an aldehyde functional group is. So the pieces that we have here are an isopropyl group, a CH2, and an aldehyde functional group. Not only that, but we know that the aldehyde functional group is attached to the CH2 because these two protons are splitting the aldehyde hydrogen into a triplet. It says 1H triplet. So there's only one way to connect all of those things. You've got the isopropyl group, then the CH2, then the aldehyde group. In other words, compound U. So the way you know this is by the chemical shifts. They give away a lot. Now on the next one, we have again 5 aromatic protons and again an ethyl group. We have a 3H triplet. That means it is a 2 H's next door. And a 2H quartet. That means there's 3 H's next door. But this time, because it says 2H, that's a CH2. This time the CH2 is at just upwards of 4 parts per million. So it's got to be alpha to an oxygen. So this is the other one of the two compounds we considered earlier. This has to be compound S. Again, remember, OET means OCH2CH3. So the CH2 of the ethoxy group is at about 4.1 parts per million. The CH3 much further upfield at about 1.3. And then you have a total of 5 aromatic hydrogens. They're the remaining hydrogens on the benzene ring. So spectrum E has to be compound S. And then last but not least, this one's probably the hardest one. We have a total of 2 hydrogens, 2 types of hydrogen in the alkene range, the vinylic range. One of one type and one of another type. both with multiple hydrogens next door. We've got complex splitting. And then we've got a 2H doublet that I would say looks like it's allylic. It's one carbon away from a carbon-carbon double bond. So you've got a total of 3 types of hydrogen in a ratio of 2 to 1 to 1, where 2 of those types of hydrogen are alkene hydrogens. There's only 2 compounds that it could be. It must be W or Y. And the way you know which it is by the number of H's in the resonance. Those 2 H's are equivalent. These 2 H's are equivalent. And these 2 H's are equivalent, the allylic hydrogens. So the ratio for A to B to C equals 1 to 1 to 1. It's 2 to 2 to 2. We don't have 1 to 1 to 1. We have 1 to 1 to 2. There's twice as many allylic hydrogens. So that means it has to be compound W. Compound W is 3 types of hydrogens. There's 2 of this type. There's 2 of this type. And there's 4 of this type, the CH2 over here and the CH2 over here. Those are all equivalent. And the ratio of A to B to C is 1 to 1 to 2. That's what we see on the spectrum, 1 to 1 to 2. Furthermore, the 2H resonance is split into a doublet. This hydrogen has 1 adjacent hydrogen, so it's split into a doublet. These 4 hydrogens do not split each other, even though they're adjacent. Remember in class we said that adjacent hydrogens do not split each other if they are equivalent. And all 4 of these hydrogens are equivalent. So that means the last one has to be compound W, not compound Y.
When you said that HC is 1 to 1 to 2, is it because there's 2 HCs on either side of the line of symmetry?
That's right. There's 2 over here and 2 over here. There's a total of 4 of them. Meanwhile, there's 2 HAs, 1 here and 1 here. There's 2 HBs, 1 here and 1 here. So the ratio is 2 to 2 to 4. In other words, 1 to 1 to 2. Is that what you meant?
Yes. Thank you.
So that's why. And now for the combination spectroscopy problem. There's no one right place to start. But I'm noticing on the proton NMR a couple of 4H resonances. That's got to be each of them 2 equivalent CH2s, because it can't be CH4. We also have a CH3 and a CH2, and then a CH over here. So it does no harm to write this down. Two times CH2, just write it down. Another 2 times CH2. A CH. And CH2, CH3. I know that this CH2 is attached to the CH3 because the CH3 is a triplet. That means it is 2 adjacent hydrogens. So fine, we have some pieces. In the carbon NMR, there are 6 types of carbon, one of which is a carbonyl. That's the only way it would show up down there. And then there's 5 other types of carbon. So let's also write down C double bond O. We know from the carbon NMR that we have a carbonyl. The IR also shows the presence of a carbonyl at about 1720. And it also shows us that all of the CH stretches are sp3 hybridized carbons. So we know there's no carbon-carbon double bonds. And from the mass spectrum, we know that the molecular weight is 126. So let's write that down. Write down everything that you know. So we need to somehow put this all together. And get a molecular weight of 126. Good first guesses at a molecular formula. You might want to remember these. Are CXHYO and CXHYO2. So let's pick one. Let's assume the formula is CXHYO. So we'll subtract 16 for the oxygen. Actually, we could just as well subtract 28 for C double bond O, since we know that that's there. But we want to find out how many carbons and hydrogens there are if we can. So that equals 110. So the remaining 110 is our carbons and our hydrogens. Well, we know there can't be 10 carbons, because 10 times 12 is 120. That's too much. We also know there can't be 9 carbons, because 9 times 12 is, let's see, 90 and 18 more is 108. That only leaves 2 for hydrogens. What about 8 carbons? 8 times 12 is 96. For 12 carbons. Looks like 14 to me. For 14 hydrogens. So that's how you figure out how many carbons and hydrogens there are. It looks like we're looking at a formula of C8H14O. Good, so now we've got a molecular formula. I doubt we'll be able to do too much more with the mass spectrum. But knowing the molecular weight is helpful. So we know there's 8 carbons and 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. We've got all 8 carbons accounted for. 1 in the CO, 2 in the ethyl group, 1 in the CH, 2 equivalent CH2s, and 2 equivalent CH2s. One thing that's kind of remarkable about this compound is there's only 1 CH3 in the ethyl group. So with this, we can start putting pieces together. Let's see if all of our hydrogens are accounted for. 4 plus 4 is 8, plus 1 is 9, plus 5 is 14. So we've got all of our carbons and all of our hydrogens accounted for. The only thing that's left is putting together the pieces. So C double bond O is 1 piece. And we know we have to have two equivalent CH2s. So maybe they're on opposite sides of the carbonyl. Actually, I left out a very important step. Looking at the formula, C8H14O, that means there's 2 degrees of unsaturation, or the index of hydrogen deficiency is 2. That means we either have 2 double bonds, 2 rings, or a ring and a double bond. We already know there's 1 double bond in the carbonyl, in the C double bond O. And the fact that we have only 1 CH3 makes it sound to me like we have a ring. So maybe the next around the ring is 2 of the CH2s. So we've got the CO accounted for. We've got 2 of the CH2s accounted for. Maybe next come 2 more CH2s. So that accounts for those 2 CH2s. And next, all that's left is CH and ethyl. There's only one way to put that together. And we've made ourselves a nice little 6-membered ring. So all we have to do is connect all of those things up. These are two equivalent CH2s. These are two equivalent CH2s. And then you have a CH attached also to an ethyl group. Or of course, you can just draw it like this. And that's the answer. So I gave you a step-by-step method to approach these problems in the class notes, but it's certainly not the only correct way to do it. One of the first things you want to do is try to figure out what the molecular formula is. Start with one of these two. If CXHYO doesn't work, then try CXHYO2. But with that structure, we've accounted for all of the hydrogens and all of the carbons. I will also just tell you one last thing. Do not memorize this answer. If there's a question like this on the exam, that will not be the answer. If you draw that structure, you will not get credit. It will be something else. And that's basically it. Sorry I went over. Any last questions?
Will this be posted on your YouTube channel?
Yes. I'm assuming it worked. Because under the, yeah, it says pause recording, stop recording. I think it's working. So as long as the recording worked, it will be on the YouTube channel. Probably sometime tomorrow.
What's your advice on like timing for the exam? Because I know that like this last question will like seems like it'll take the longest. So like would you advise to save that one for last, or like what would be your advice?
Um, well, you don't, I could see you doing it either way. I could see you doing it first, or I could see you saving it for last. It might be best to save it for last,
Okay.
because there's only 50 minutes.
Mm-hmm.
Could you re-explain how you knew a benzene ring is present in the E proton spectrum? I knew a benzene ring was there because of the chemical shift of these hydrogens. Aromatic hydrogens typically show up around 7 parts per million. And I also see that there's 5 of them total. That tells me that there's a benzene ring with one group attached. There's a total of 5 aromatic hydrogens. 1, 2, 3, 4, 5, and then something else, some other group. Is that what you meant? Yeah, I would say I knew it from the chemical shift and from the integrals, but mainly from the chemical shift. Other questions? Let me at least see if I have a cat for you guys to reward you for sticking around for so long. I was hoping he'd be on the bed. Where'd you go? There he is. I found him. Here he is. I don't think he
Very
wants.
cute.
I don't think he wants to be held right now. He was very comfy out there. He's trying to get down. So that's my kitty. Actually, he doesn't seem to mind my holding him right now. All right, well, I will see you guys on Wednesday then. Let me put him down. And like I said, as long as everything worked, this will be up on YouTube sometime tomorrow. I'll send an email. Probably sometime in the morning. My cat was interested in humors. That's pretty good.
Have a good night, Professor.
Yep, see you all on Wednesday.